All right, I'm ready to take questions. Who's got questions? Welcome to office hours. Let's see, who's in the house? Jaden, Jonathan, Stephen, and Rebecca are in the house. So,
So I'm about to head upstairs where I'll be able to find this particular one if I can't find it by referencing it this way with you. But I think it was on test two. There was a proof involving um, numbers that don't divide. I think on maybe the second page, so maybe about five or six or so.
that's right.
Um, and I think that in the feedback, you gave me a recommendation to try proof by contradiction. I think.
Probably proof by contrapositive if it was a does not divides.
Hmm,
So you took form B probably of that
that
test,
sounds right.
and I think you're looking at problem number 6, test 2, form B. Problem number 6, it goes something like this. For all A, B, and C in Z plus, because I didn't want to have to deal with not zero, but even if it is zero, it would be false hypothesis and we don't have to worry about it. If A squared does not divide B squared plus BC, then A does not divide B or B does not divide C. Now, we actually looked at this problem. It also appeared on Form A as well. Let's see what problem number it was on Form A. Same problem number, same problem. And we did look at this either last night or the night before. I think we looked at this on Wednesday night. But
Oh, my apologies. I watched a couple of the office hour recordings, but maybe I missed this one. Um, I
yeah,
think I see. So maybe I'll just kind of
I
talk
mean,
out loud through
so
my idea for a
yeah,
second.
yeah,
You would so
you
if
can use
contrapositive,
you
you would
can use
say
that, or you can use contradiction, but contrapositive I think is a little more straightforward. Why don't we write the contrapositive,
sure.
Jonathan? What is the contrapositive?
So if A divides B or B divides C.
I think this
Oh,
or
thanks.
should change to an and.
That seems right. Yep. So if A divides B and B divides C, thanks for that.
Mm-hmm. You'll need them both.
Then A divides or A squared rather, sorry, divides B squared plus BC.
Yep. And with both of these pieces of hypothesis, you will get enough proof money to prove this. The interesting thing about this particular problem is it isn't that A divides B and A divides C. It's that A divides B and B divides C. So it takes a double substitution to get enough copies of A to factor an A squared out of B squared plus BC when you start trying to say something smart about B squared plus BC.
Hmm. Mhm.
So in a proof by contraposition or by contrapositive, you can say it either way. If we assume A, B, and C are in Z plus, again, it doesn't really matter. Z is fine. We're going to assume A divides B and B divides C. Making these assumptions includes the assumptions that A and B aren't zero. They won't be as long as, these are all coming from Z plus. But even if it just said Z, this assumption includes the assumption that these expressions are defined. What do we wish to show?
And I wish to show that consequence. So A squared divides B squared plus BC.
Right. So let's hear the voice and apply the definitions. What do we get from our hypothesis? What kind of equations do we get?
Um, well, from the definition of divides, right? We can say B equals A times, let's say, D or something like that,
Yeah, A times, you want to say D, okay.
or
Where
divisor.
I like it, where D is in Z.
Mhm. And then similarly, we can say something about B dividing C. So C is going to be equal to B times, let's say, uh, G, because I don't want to use E or F.
That's fine. So we've got some good proof money here. Let's take a closer look at our wish. What is it we really wish to show? In other words, what kind of equation are we going to need to establish right before we will be able to say that a squared divides the quantity b squared plus bc?
Hmm. Um, One that's similar to the ones we just set up. So we're going to want to say, what is it, B squared plus BC equals A squared times,
I
say,
like using,
H.
okay, I'm
M.
going to use
M is
m.
good.
I do usually reserve my m for that, but h is fine. It doesn't really matter as long as we don't use any of the letters we've already used. So, here's our wish as opposed to our proof money, but our wish is really nice because it tells us, oh, we got to say something smart about this expression, b squared plus bc, as opposed to leaving our wish in this formulation, which might lead us to think that we need to look at a squared. And not really. We're going to try to factor out an a squared, but we need to look at b squared plus bc.
Hmm.
So what do we do from here?
Um, well, we can start doing some substitutions like you'd suggested. Um, so one thing we could do is replace our B's or replace our C's. So let's do B's first.
Okay,
Um, so so B squared plus BC is going to be equal to AD quantity squared
nice,
plus AD times C.
good.
And
And we,
then on
mm-hmm,
the next line, we could replace that C
mm-hmm,
um, with BG.
okay. And if we take a close look at what we have here, we have an a squared d squared because this power of 2 does distribute across the factors. And we do have an a squared in the first term, but we don't have an a squared in the second term. We only have an a. That's not enough. So how are we going to remedy that?
You would turn that last B into AD.
Yeah, we've got another application of that equation that b equals ad. So we've got plus ad times ad times g now. Adage almost. So we've got a squared d squared plus a squared d squared g. And now we see that we have enough a's to factor an a squared out of both of these terms, and that's what we were shooting for. What do we do now? You see, we've got part one of the definition of divides done.
I have a question.
So we got part one done, but we
If
still
you
have to deal with part two. We've got to talk about why this m is an integer, right? We still have to, say a few words about why this expression d squared plus d squared g is actually an integer.
Because we denoted that AD and B and G are already integers earlier before back using when we stated the definition of divides. We
Close.
just said,
That's very close. Um, we did use the fact that B equals AD, and we used the fact that C equals BG. What we haven't used is the facts that D and G are integers. It is true that B and C are integers, but right now we're not seeing B or C in here. We're seeing D's and G's. So we need to use the fact that D and G are integers. We need to burn this proof money to get part two of the definition of divides. We use part two of the definition of divides. You see what I mean?
okay.
That's always the game in mathematics. So if you've got a multi-part definition to satisfy, you will generally satisfy those parts in concert. In other words, to find that part one worked out for b squared plus bc. In other words, to get the b squared plus bc equals a squared times something that we're calling m, we used part one several times with substitution. To get the part two, that the m that's sitting here and here is an integer, we use part two. That's what I mean by using these parts in concert. So we simply go ahead and use those. Since D is in Z and G is in Z, M, which is this quantity, D squared plus D squared G, is in Z. Why? You want to get every point you can, folks. Why do we know M is in Z, everybody?
Because the sums and the products of integers are integers.
That's exactly right, Jaden. Beautiful. Because sums and products of integers are integers. This is worth looking at twice if you get my drift, folks. So, in fact, b squared plus, if you have time, I don't think I would take anything off if you're out of time and you just need to move on to the next problem. But if we go ahead and say, so b squared plus bc equals a squared m, where m is in z, which means a squared does divide b squared plus bc. By definition of what, folks?
Divides.
Yeah, nice. And that is a full credit proof right there. So yeah, I like these does not divide type statements because it allows me to check two things. One, do you understand proof by contrapositive or proof by contradiction? It can be proven by contradiction. Two, do you understand the definition of divide? And three, are you able to carefully read the hypothesis and get the correct equations here? It was a 4-point deduction if folks did not use the fact that B divides C. A lot of people just said, oh, A divides B and A divides C. Well, that is one kind of problem that you might be given, but being able to read is important, right? So getting the correct equation here and realizing that there's a double substitution to be made into this particular B is helpful. Oh, excuse me, into C, my bad, into C. There's a double substitution into C. First it's BG, and then it becomes ADG. Yeah, it was C that took that double. So thank you for that question, Jonathan. It's a good one to keep in the back of our minds.
I
Rocky?
got a question about that.
Yes, Stephen.
Yeah, so you see, like the part one of the definition of divide, right?
Uh-huh.
Where we have the a squared plus d squared plus ad bg on the third line. Yeah, so how did that the ad move change to like adg?
Yeah, that's a great question. So let's make this a little bit more explicit. We're really looking at what's going on with that B, aren't we?
Mhm.
But look what B is equal to.
Oh,
See it?
Mm-hmm.
Okay, so we used this. It's kind of beautiful. Proof money doesn't really get spent. You can always spend it again. And with this
I get it.
hypothesis, we do need to spend it again.
Mm-hmm. Yeah. Thank you.
Mm-hmm.
Thanks for walking through it.
Yeah, I saw that in the chat. You're welcome, Jonathan.
I'm so sorry about it, the call dropping on you. But
Hmm.
I have another one that at least gave me some trouble over the semester that I would appreciate some extra work on,
Sure, what is it?
if that'd be all right. So I think the next one actually in the in test 2. So it's number 7. If n is in Z, then n squared plus n minus 3 is always odd. And I think that you worked on a similar type of problem the last couple of days. I was hoping um, so the recommendation that you gave me on your feedback is to try proof by cases. Thinking of this as like I need to be thinking about looking at odd as being some sort of partition or suggesting a partition. And then that gives me the opportunity to deal with it by cases by looking at the partition it makes. Am I kind of thinking down the right path here?
You really are.
Okay.
Because let's just think about what would happen if we did not have a way to introduce a 2 into this game. Because the definition of odd requires that we show n squared plus n minus 3 equals 2 times an integer plus a remainder of 1. Does everybody see that? We're dividing by 2, and we're saying, hey, if we divide n squared plus n minus 3 by 2, we should get a remainder of 1. Well, there's not a 2 to be seen in n squared plus n minus 3. Okay, not quite true. We could change -3 into -4 plus 1. We'd have a 2 in the -4.
Mm-hmm.
But there's no 2 apparent in n squared plus n. And by introducing proof by cases, we know for a fact that n squared plus n minus 3 is an integer. It's in Z, right? Because n is in Z, and this is just an expression involving operations under which Z is closed, right?
Mm-hmm.
Multiplication, addition, subtraction. So the fact of the matter is this expression, n squared plus n minus 3, is either going to live in 2Z or it's going to live in 2Z plus 1. QR theorem says you can divide that expression by 2, one way or another, and you're guaranteed of getting either a remainder of 0 after you do that division, or you'll get a remainder of 1. Rocky, calm down. He has been full of himself when I get onto Zoom. It's interesting. So we want to prove that this expression is always over here in this partitioning set. It's a congruence class mod 2. Basically, remember, A is congruent mod 2 to B if and only if A mod 2 is equal to B mod 2. In other words, we get the same remainder when we divide A by 2 that we get for B when we divide it by 2. That's what this means. That's exactly what it means to say A and B live in the same class. Either they're both even or they're both odd. It turns out this always turns out to be odd. But this is, So all of these proofs by cases that we are dealing with, except for the set proofs where, union gives us a proof by cases. And sometimes Tarski's world, we have an or statement that gives us an argument that we need to make in cases. a predicate that involves or. But straight up proof by cases, where the point of the exercise is a proof by cases, for this course is always going to be a proof based on QR theorem, where we're dividing by a particular divisor and examining the remainder. Rock, hush. Might have to find a meaty bone in the freezer and hush him up, but I really don't want to reward that behavior. So remember, when we're doing proof by cases, we have a couple of steps that we want to investigate or execute, really. Step 1, discover the divisor D. Where do we look to find D? Look at the conclusion. The conclusion will give you enough clues to tell you what D is. Here, we're being asked to prove something is odd. Oh, that means when we divide it by D equals 2, we're expecting this particular remainder. The remainder R equals plus 1. So look at the conclusion, or look to the conclusion.
So what would this look like if the divisor was 3? Like, what would the conclusion look like?
Okay, let me give another example. If n is in Z, then n squared equals 3k, or n squared equals 3k plus 1, where k is in Z. This is a problem that we worked in class. And when we look at this conclusion, we're saying, oh, if we look at n squared and divide it by 3, we're either going to get a remainder of 0. In other words, n squared is a multiple of 3. It's 3 times k. Or a perfect square, n squared, is going to give us a remainder of 1 when it's divided by 3. In other words, this statement says when you divide a perfect square by 3, you will never get a remainder of 2. So here, D is 3. Another example, we looked at this last night or the night before, maybe last night. If n is Z, then 3 divides the product of 3 consecutive integers. In other words, 3 divides this. Well, D is still 3. We're just saying when we look at this expression, this product of 3 consecutive integers, and divide it by 3, we get a remainder of 0. In other words, it's actually divisible by 3. So here are 2 examples of statements where the divisor is 3. Does that help?
Yeah, that makes it a lot more clear. Thank you.
Yeah, I mean, we could even do another one. If n is in Z, then 4 will divide the product of 4 consecutive integers. And so we did write this proof last night, and you can look at the notes. We did this one in class. You can look at the notes. And this is an interesting one because the conclusion is a disjunction. It's an or statement. And in different cases, we might get this, and in other cases, we might get this. The most common error that students make is thinking that the remainder that is being applied in a case to the object n, the integer n, will be the same remainder that is obtained when we look at the expression, and that's simply not true. N, if D is 3, could look like 3q or 3q plus 1 or 3q plus 2. There are 3 different possible remainders that n could yield. But in each of those 3 cases, this expression n times n plus 1 times n plus 2 should give us a remainder of 0 when it's divided by 3. Same here. There are going to be 2 cases. We're going to apply the divisor D to the integer n, and that means when we apply the divisor 2 to n in step 2 of our algorithm on how to deal with these, apply the QR theorem with that particular divisor D, to the integer in the hypothesis. In other words, set up the cases as opposed to discover D, which is the first step. You can't really set up the cases until you figure out what D the cases are going to be based on. But the point is, N could look like 2Q, or, if it's even, or N could look like 2Q plus 1 in the case that N is odd. We just simply don't know that. We don't know which N is. We know it's an integer. We know we can divide it by 2. Well, we're guaranteed one of 2 possible remainders. In both of those cases, we want to show that this expression yields a remainder of 1 when it's divided by 2. See what I mean? So even in the case when N is even, this expression we're interested in is going to turn out to be odd. Does that help?
Yeah, that's pretty helpful.
Just
Thanks.
trying to head you off at the pass, because again, the most common misconception is that somehow the conclusion is, its congruence class mod, D would match the congruence class of N in that particular case, and it doesn't. They're not independent of one another, but it's not a one-to-one correspondence. So if we go back to number 7, I mean, the solution is online, right? The solution is online, but we just to remind you, if we're going to set up the proof by cases, give yourself the integer, and then to set up the proof by cases, we say a little extra, the QR theorem, just invoke the QR theorem. We're not proving it, we're just using it. With D equals 2 says, either N is equal to 2Q. In other words, either this N that we're looking at is even, or N is equal to 2Q plus 1, where Q is in Z. And that gives us our 2 cases. So just remember to invoke your QR theorem to set up your 2 cases. And in each case, in both cases, here it's just 2 cases, right? So I'll say both cases. But in all cases, you would wish the same thing. And here we wish to show that N times, that N squared plus N minus 3 is equal to 2K plus 1, right? We want to show it's odd. So I'll put a line here just so you realize we're going back to number 7. So you just crank it out. You simply look at this expression and you plug in 2Q in case 1. You'll be able to rearrange things and be clever about the -3 so that we get this looking like 2 times an integer plus 1. Then you turn around and do the same thing in case 2, substituting in N equals 2Q plus 1 for this quantity N. You'll still be able to reduce it and rearrange it so it looks like 2 times an integer plus 1. Okay.
Makes sense. Cool. Thanks.
So I will forego taking the time to write those cases out because we did one of these last night and there are solutions available in the test folder. All right, who else has got a question? Let's hear from somebody else here in the room tonight.
I think it was after exam 3, I was talking to you, and I think you were talking about how, like for the set theory problems, we didn't see one with a empty set, unless I'm like misremembering. And you
Yeah,
said that we,
I will not ask you to prove that a set is empty. There's only so I don't mind telling people that if you're bothering to come to office hours, I can say, hey, you're not going to see a set proof where you have to prove something is empty. I can say that, but you will see either a set equality proof or a subset inclusion proof. Let's see if I can get out of my own way here and show you. Rocky, I say good Lord. This is test form 3B.
Mhm.
And so this was the Monday, Wednesday class. Generally, the Monday, Wednesday class was Form A, but things got kind of skipped around. So Tuesday, Thursday did not include a problem from section 6.2, but the Monday, Wednesday class did. And here is the type of subset inclusion proof that I gave from section 6.2. You can expect something similar. So I'm really giving you a lot of it. You know, I'm trying to help you out here with this by just making it a fill in the blank. I don't tend to, like fill in the blanks that much,
Is
but
there any chance we get another fill in the blank for the final tomorrow?
yeah, it's a fill in the blank subset inclusion proof.
Oh, okay.
It's not going to be this one,
Okay.
but it's going to be, you do have to know what intersection and union and set difference and set complement and subset mean, right? You do need to know the basic strategy for proving subset inclusion. It's called an element chasing argument. If we want to show that this set on the left is a subset of the set on the right, we take an element from the set on the left and we chase it literally until it lives in the set on the right. See what I mean? So you need to know that much because I set it up where you have to tell me where X is going to start out and where we wish to find X does actually eventually live, you see.
Okay.
So you
Thank
have to understand the structure of a subset inclusion proof. Um,
Could we go through one of those?
sure.
you. Did you, I thought you posted a office hour video about that exact problem, or was it a different one?
No, we walked through that particular problem. Thanks for pointing that out. But we often redo things. People come and they're here now. And I can make one up on the fly here. Um, so for subsets A, B, and C of a universe or a universal set U, prove. All right, so let me just think for a minute. See if this is even true. Is A union B minus C, is that a subset of A minus C union B minus C? In other words, does union left, no, excuse me, does set difference right distribute across union? That's really what we're asking. All right, so, we can check to see if this is even true by using Venn diagrams to figure out what these sets look like. All right, so let's just think about it. If we want A union B minus C, so I'm going to draw A. You always draw these bigger than you think you should. B and set C. Okay, so here's A. Here's the circle for set B, and here's the circle for set C. They're all living in a universe. So A union B, if we shaded that, it would be everything that's in A or in B. But then we're subtracting C away from that. So I think it's going to be these regions. Do you agree? Which this is the region that's A union B minus C.
Yeah.
Kind of I thought about, all of A union B and then took away anything that was in C. And that left me with these three regions. All right, so if we want to figure out what this set is to see if, this is even a true statement, Some of these can be a little tricky. Sometimes you think they're true and they're not, and that's why I want to check this before I try to prove it. So this is a union. So we're going to figure out what A minus C is. We're going to shade that. And then we're going to figure out what B minus C is, and we're going to shade that. And the grand total will be A minus B union, A minus C union B minus C. So A minus C. So here's the circle that's A, but we want to cut out this cat's eye that it shares with C. So this region, right, these two regions are A minus C. Do you agree? So we want anything that's in those two regions or in B minus C. Well, B minus C is all of B, subtract the circle that's C. So it's that part gets shaded twice, but we don't care because union is inclusive. So it is this is a true statement. See how the two regions are the same that are shaded? So this is a reasonable proof to try to write. So how would we start this? Obviously, we're going to assume A, B, and C are subsets of U. Now, the meat of the matter. We want to show that any element that is in this set on the left is an element of the set on the right. In other words, if X is in this set on the left, then X is in the set on the right. So what should we assume, everybody? We're chasing an element around. We have to have an element. I like to call them X, but you could use any letter to represent your element. You're scaring me.
So let's assume X is an element of A union B, quantity minus C.
Thank you. Everybody following that we're taking an arbitrary element from this set here? And then what do we wish to show?
Well, we're going to want to show it's an element of that big old set on the right.
That's
Only
exactly
A minus
right.
C, quantity union B minus C.
Well said. Does everybody understand that that is the nature of the beast for subset inclusion? We're going to take an element from this set and chase it into this set. The key to these proofs is to realize that as we deconstruct what it means for X to be in a particular set, we reverse the order of operations. What am I talking about? If we were just going to build the set A union B, quantity minus C, the first thing we would probably do is figure out what A union B is, and then we would take that union and subtract C. That would be the last step, would be subtracting C. When we're deconstructing what it means to be in the set, we start by deconstructing the meaning of that last operator that is executed. So we break down the set difference first. So since X is an element of the quantity A union B minus C, we're going to deconstruct, or at least, we're going to examine what that means for X to be in that set difference. So what does it mean for X to be in this set difference, folks? X is in something and X is not in something. What is X in?
A union B.
Nice. Thanks, Rebecca. And what is X not in?
C.
And this is by definition of?
Set difference.
Exactly. So we've just broken down what it means for X to be in that set difference. We cannot break down that X is not in C any further. That's what we call an atomic statement, okay? But we can break down what it means for X to be in this union, and that will be our next step. Since X is in A union B, that means what, folks? What does a union operator mean?
X is in A or X is in B.
Thank you. X is in A or X is in B by definition of union. And this is an or statement. These are atomic statements, but we don't know which one we've got. We might have both, you know, but in which case we'll be proving the conclusion that we wish twice for the X's that are in both. But we have no guarantee of that. We do know X is definitely in A, or, so that'd be case one, X is in A, or case two, X is in B. So now we have cases. In both cases, this fact that X is not in C is still going to carry. It's going to carry through both cases. In both cases, we want to show X is in this set. In both cases, we wish to show that X is in that union of those two set differences. All right, so case one. Let's suppose the hypothesis of case one. We're going to suppose X is an element of A. Now, it can be helpful to take a look at the wish and break it down a little bit. I mean, we want to show that X is in A minus C union B minus C. The last operator that would be executed if we were constructing this big set would be this union. So we want to show that X is in A minus C or X is in B minus C. That can be more thinking notes. If we can get X is in A minus C, then it'll be in this union by definition of union. If we can get that X is in B minus C, then it'll be in this component, so it will also be in the union by definition of union. So in case one, we've got that X is in A. Which of these two do you think we're going to get out of this game in case one?
The one on the left, I reckon.
Yeah, that X is in A minus C. Well, we're going to have to argue why it's in A minus C. We've got that it's in A, but don't forget, and that's why I like to put squares around, you know, what we've got in our hand. We know X is not in C in both cases. So we still know X is not in C. So X is in A minus C by definition of what?
Set difference.
Yep, good. It's in A, it's not in C. That puts it in A minus C. Thus, X is in A minus C union anything else, including B minus C, by definition of what?
Union.
Yep. And that completes case one. Namdi, did you ask for this one or was it Jaden?
It was me.
Okay, are you following this, Namdi?
Yeah.
So what's our hypothesis for case two then?
So I guess we would suppose that X is an element of, or we would suppose X is an element of B, and we still
Mm-hmm.
know that I equals C.
Mm-hmm. Suppose X is an element of B. We still know X is not in C. Now what happens, Namdi?
So then, X is an element of B minus C by definition of set difference.
Yeah. And then
Sorry, the
what?
only reason I was speaking is because I was like writing this all down.
Oh, you're fine. So we've got what we want. Thus, X is an element of, doesn't matter which we put first, it's in B minus C, but it's in B minus C union A minus C, so we can write it in either order. Might as well write it in the order it's written by definition of union. You know, so we showed that X being an element of, well, where do we start? We started with X an element of A, B quantity minus C raw. Oh my gosh, you're fired. Sorry, folks. Got dog on the loose. I don't know what's wrong with him lately. I think he hears me speaking.
Mm.
You know, I don't know. We're just
You could put your assistant on a pip.
rock, rock. Here's my rock. And my messy, here's my office. My dining room was turned into my office. Rock out. Who's a good
Oh, what a cute
boy?
guy.
He is. He's my old handsome boy. He's my boy. All right, Rock, you're a nuisance. I love you. I can't put him outside. He would just howl. And I wouldn't do that anyway. We showed X as being an element of A union B minus C implied that X is an element of A minus B union. Oops, typo. What should I have written there?
Should be A minus C union B minus C.
Thank you. So, in fact, A union B minus C is a subset of A minus C union B minus C by definition of subset. It just fits. How horrible. But it does fit. So we'll call it a win. Does this help, Namdi?
Yeah, this helped a lot. I think this was like, out of the three exams I was looking over, like the solutions and the notes that you gave me, this was probably like the problem I had the most problem. Or
All right.
just set theory in general gave me the most problem.
So you can check out the video. In the video descriptions in YouTube, you'll be able to just read the descriptions and figure out which one we looked at this subset inclusion problem from the test.
Okay.
So you can see another one. There's another one. All right.
Thank you.
Next up, who's got a question? See who straightened out. Make sure this is still in focus.
I have a question. Are we gonna see factorial on our final exam?
I'm going to say be ready for factorial.
All right, can we go over factorial?
Mm-hmm. So recall N choose R. It's kind of nice just to know what it really means. It's the number of distinct, that means different, of course, subsets of size R that can be taken from a set of size N. So I think our example, it turns out to be just the right size to think about what this really means, is to look at an urn or, a bowl. It's got 5 balls in them. We can number them 1, 2, 3, 4, 5. And so we could ask, what is 5 choose 3? Well, it would be the number of subsets of size 3 that we can find from a set of size 5. So here's just this nice kind of classic set of size 5. And just imagine we're going to reach into that urn and we're going to pull out 3 balls. And that's going to be a subset of size 3. Remember when we did this in class?
Yeah, I think so. I remember.
Yeah, and so we actually went through the exercise of counting, how many different ways can we reach into this urn and grab 3 of these balls and come out with a set of 3 balls that we haven't pulled out before. So we could pull ball 1, ball 2, and ball 3. Or I'm just going to try to do this lexicographically. Ball 1, ball 2, and ball 4. What would be the other set of 3 balls that has the 1 and the 2 ball in it?
1, 2, and 5.
Exactly. All right. Or now that's all the sets of 3 balls that involve 1 and 2. So the next thing to do is to not change the last one, but change the second to the last one. Let's just change the 2. So 1, 3, and 4 is possible, right? That's different than any of these we've done so far. What else? Just keeping along these lines.
1, 3, and 5.
Yeah. And that's it for 1, 3. So then we can say, oh, 1, 4, and what?
1, 5.
Yeah. All right, so we're done with 1. Notice how 1 appears in half of them? Oh, well, you don't know it's half of them. Oh, no, it's a little more than half of them. Oh, that's interesting. That is interesting. Huh. Now, wait a second.
Can you share the aha?
Yeah, I'm trying to figure. I mean, because if we're counting the number of subsets, you know, number of size 3 subsets, the problem with doing it this way, where we've got 5 choices for the first ball, then the next ball we've got 4 choices, and the next ball we've got 3 choices. The problem with taking that as the number, it's too big.
Couldn't you do it? There's a different way. Whenever you do and choose R, couldn't you just all plug it into the formula with whatever
Yeah,
numbers we're given?
yeah.
Yeah.
But the
Fact-
point is, if we pick the 1 ball, the 2 ball, and the 3 ball as our, 5 choices, 4 choices, 3 choices, we might have gotten that when we picked the 3 ball first, then the 1 ball, then the 2 ball. The point is, there are 3 factorial ways to arrange these. So this is 3 factorial or 6 times too big. It's 10. So yes, the formula for n choose r, it is the n factorial divided by r factorial times n minus r factorial. I've already I've already I've already gotten rid of the n minus r factorial because I didn't say times 2 times 1 here because I stopped because this is, choices for the first ball times choices for the second ball times choices for the third ball. So I didn't go all the way down to choosing all 5 balls. So that's why this doesn't look quite like this. This, you see the n factorial, uh, but not quite, you see, because we don't have all the way down to 1 factorial. So we've already gotten rid of the n minus r factorial by this process. Anyway, let's finish it up. We should have 10, okay? So give me the next 3 that we could pull.
Um,
It's interesting.
oh,
See, you'd think that half of them would have the 1 in it and the other half would not, but it's not quite like that.
so you would start from 2. Now,
Yeah.
so you just go 2, 3, 4,
Mm-hmm.
and then you use 2. I can use 3 input just for 5,
Mm-hmm. Nice.
and then do I continue with 2?
I think so. Because you can change the 3.
So you do 2. Oh yeah, so you do 2, 4, 5. And then here you would go 2, or do we go 3, 4, 5?
Mm-hmm. That's it. There are
Exact.
10. Mm-hmm. All right, so 5, choose 3. Is 5 factorial divided by 3 factorial times 5 minus 3 factorial. So it's 5 factorial times 3 factorial times 2 factorial. But if we want to simplify that, we just take the big one, which is the 5 factorial. That's 5 times 4 times 3 factorial over 3 factorial times 2 factorial. The 3 factorials cancel. We're left with 20 over 2, and that's 10. So one of the things that I challenged you to do was because some folks bent the rules a little bit and used this nifty little fact when they did a special homework or a take-home quiz. I think it was N choose R is actually equal to N choose N minus R. All right, let's think about it with the 5 and the 3. 5 choose 3 is the same as 5 choose 2. The 3 and the 2 add up to 5. Why is that true? The reason that's true is because choosing 3 from the 5 is the same as choosing the 2 you are not going to choose. But theoretically, to prove that, right, isn't that cool?
Well, this is generally true. I guess.
Oh yeah,
Wow.
we're gonna prove it now. It's easy to prove.
Let's do it.
All right, just remember that N is greater than or equal to R, and R is greater than or equal to 0. And they could both be 0. You know, how many empty sets can you choose from the empty set? 1. 0 choose 0 is 1. Okay. So let's do it. All right, so N choose R by definition is N factorial over R factorial times N minus R factorial. We'll just leave that because that is the given formula for N choose R. Well, we'll apply the same given formula to N choose N minus R. All right, so it's the top one factorialized over the bottom, which is N minus R factorialized, times N minus R factorialized, right? The top minus the bottom factorial. This is what goes is. But what is that? Well, it's
Oh my God.
See it?
That's nice.
Isn't that pretty?
Oh.
Because N minus N, of course the N's cancel, but minus a minus R is an R factorial. These are the same thing because it doesn't matter which order these two factors on the bottom are written. So that's the proof that those are always equal. The greatest application that we didn't get to is the binomial theorem. Have you ever tried to expand like x plus y to the 5th? And how hard, who wants to do it? Nobody. We don't even want to square it for crying out loud, much less raise it to the 5th. But this is the thing to understand. When we are expanding this, when we're actually distributing all these together and figuring out, oh, there's going to be an x to the 5th term, right? Because this x times this x times this x times this x times this x is going to give us the x to the 5th. And at the end, there's going to be a y to the 5th term because this y times this y times this y times this y times this y will be the y to the 5th. But there's a bunch of stuff in between. And for each of the terms in between, we can simply ask ourselves, how many different ways can we build the term that looks like, say, x raised to the n minus r times y to the r. But here it's 5. So, and how many ways can we build the term that looks like x raised to the 5 minus r y to the r? For example, if r is 3, we're trying to build x to the 5 minus 3 y cubed term. In other words, we're trying to build the x squared y cubed term. But there's a bunch of ways we can build the x squared y cubed term. It pops up a lot. How many times? The binomial theorem uses N choose R to count how many different ways we can get this term that looks like x squared y cubed. It goes like this. We have 5 parentheses. From each parentheses, we're either going to choose an x or a y. To build this term, we have to pick 2 x's and 3 y's and multiply them together, and that gets x squared y cubed. So let's just think about how many ways we can pick 2 x's and 3 y's. All right, so we could pick the first 2 to be the x's And then the last three would be the y's, and that would give us one of the x squared y cubes. But we could pick the first and the third to give us the x's, and the other three to give us the y's. Or the first and the fourth to be the x's, first and the fifth, second and the third. See what I mean? So basically, we've got 5 sets of parentheses. How many ways can we pick 2 of them to give us the x squared? The other 3 will automatically give us the y's. Or equivalently, we have 5 sets of parentheses. How many ways can we pick the 3 of them that are going to contribute the y cubed? The other 2 will give us the 2 x's. So the coefficient for the x squared y cubed term is we have 5 sets of parentheses, choose the 3 that are going to give us the y's. So when you think about it, then to get x to the 5th plus some numbers of x to the 4th times y to the 1 plus some number of, say, x to the 3rd y squared plus, I'm leaving room here, plus some number of x squared y cubed plus some number of x y to the 4th plus some number of y to the 5th terms. These coefficients that tell us how many of each of those we can get are 5 choose 0, 5 choose 1, 5 choose 2, 5 choose 3, 5 choose 4, and 5 choose 5. Don't pick any
That's really
y,
nice.
isn't it? Don't pick, yeah, to get the x to the 5th term, we're picking none of them to contribute a y. We don't pick a y from any of these. So we get all x's, and that multiplies together to make x to the 5th. There's only one way to do it. Just don't pick any y's. 5 choose 0 is 1. Now, how many ways can we pick one of these parentheses to give us the y, and the other 4 will give us the 4 x's? Well, there's 5 of them. So you can pick this one, or this one, or this one, or this one, or this one. 5 choose 1. There's 5 ways to build x to the 4th y. 5 choose 2 is 10. 5 choose 3 is 10. Because of the symmetry, 5 choose 1 is the same as 5 choose 4. We just proved that because 1 and 4 add up to 5. Choosing 1 is the same as choosing the 4 you're not going to choose. So this is 5xy to the 4th. And then, of course, there's only one way to pick all 5 of them to contribute y. Just pick the y from all 5 of them. So there's my lecture that you didn't get during the semester on the nicest application of choose R. It's to give us the coefficients if we want to expand something that looks like this. Now, an interesting proof and a challenging proof is to try to relate these coefficients to Pascal's triangle. Maybe you even saw Pascal's triangle when you were in high school. 1, 1, 1, 1, 2, 1. See, you add those to get the 2, and then you add these to get 3. So 3, 3. The 1s are always on the outside. And then this is 4, 6, 4. Remember this? 5, 10, 10, 5. These are the coefficients for x plus y to the 0. This is the coefficients for the x and the y when it's x plus y to the 1. What, Rock? These are the coefficients for x plus y squared, and these are the coefficients for x plus y to the 5th. Anyway, so it's an interesting game to play to relate x n choose r to n minus 1 choose r minus 1 or r plus 1. And it's not even quite that. That's not quite right what I just said, but. All right, so do you want one that you might actually see as a problem? Simplify. Don't you hate it when you ask a teacher a question and then they give you this whole long thing that you didn't even want? N plus 1, choose n minus 1. We got a set of size n plus 1. We want to figure out how many ways we can find a subset of size n minus 1. Well, the thing to do is simply use the formula. It's n plus 1 quantity factorial on top. It's n minus 1 factorial times n plus 1 minus the quantity n minus 1 factorial, right? Because it's n factorial, r factorial, n minus r factorial. So we're just really careful when we distribute this minus down here. The n's will always cancel, and if you get anything negative, you've done something wrong because we don't have factorial defined for negative integers. It is defined for 0, folks. 0 factorial is 1 by definition. But anyway, the n minus n goes away, but 1 minus a negative 1 is 2. So then what do we do to simplify it? We realize n plus 1 is bigger. So it's equal to n plus 1 times the integer right before that, which is n, times the integer right before that, n minus 1 factorialized. Why did I stop there? Because that's far enough for us to cancel top and bottom. So we get n plus 1 times n over 2. And this will always be an integer, even though we're dividing by 2. We know one of these is even.
So starting up, we have n plus 1 factorial over n minus 1 factorial, n plus 1 minus n minus 1 factorial, but the n's cancel each other out, and then the negative times the negative turns into a positive, so it's really just 1 plus 1. So plus 1 factorial, and then we still have the n minus 1 factorial, but on the top,
Yeah.
n plus
Good.
1 factorial is really, n plus 1 factorial is n times n minus 1 factorial.
Yeah, because n plus 1 is here. The integer right before is there. The integer right before that is n minus 1, right? So we can expand and look at what n plus 1 factorial really means. We know it's n plus 1 times the integer before, times the integer before that, times you're right, times the integer before that. But once we get to n minus 1, we can just stick the factorial there, and we know that all those factors will cancel top and bottom. We've gone far enough.
Going far enough just to cancel it and then just to go ahead and simplify it.
Exactly.
Yeah, okay.
So there are numerous do laters in some of the office hours. Oh, I think we looked at this a week ago, Friday on the 5th. Just take a look.
On the final, would we expect to see like an n squared chooses n minus 1 or something like
No,
that?
no.
Okay.
No, I'm not even sure I would know quite what to do with that. Theoretically, it's certainly possible.
Any chance on the final we would see a standard factor form problem?
You could. It's possible. Do you need to see a standard factored form problem?
Yeah, I was going over them. I was hoping to see one on the final, to be honest.
You're hoping, oh God, the focus is horrible there. God, I hope the focus got better later.
I'm a little bit confused about the
Yeah,
seeing
n-choose
if it's
r. Yeah, sorry. Let me just say 12.5, simplifying n-choose r formula. Okay, so you can check out that video if you need some more. All right, go ahead. Go ahead.
I think it was on test 2 when it's is the SSF going to be a perfect square or not?
Yeah, so that was an interesting thing that we learned. We learned some really interesting facts about perfect squares and perfect cubes. We learned prefect. Perfect squares and perfect cubes. Don't worry, the binomial theorem will not be on the final, okay? So I just want you to understand, this is not on the final, but it's a good thing to understand. Okay. Anyway, perfect squares and perfect cubes. What we learned was this. If, suppose, n it's got to be big enough. So say greater than or equal to 4 is a perfect square. all the exponents in its standard factored form are even. That was one fact that we learned. So let's just look at y. If n is a perfect square, then n equals x squared, where x is at least 2, because I've made sure n is big enough. So if x is at least 2, it's got a standard factored form. So x is p1 to exponent e1 times the next prime that appears in x to the e2 times, keep on going, up to the biggest primes, call it p sub k, that is a factor of x raised to some exponent e to the k, and x is getting squared. And so what we did was we realized, oh, we can apply standard factored form to the square root of n, which is this x. Nothing, we can write it as a product of powers of primes. And then since x squared is what is in, when we square this whole thing, these powers, well, this power of 2 gets distributed across all these factors. That's just a law of exponents, that if you have a product being raised to a power, here the power is 2, that exponent, that power, can be distributed across the factors. Then we just use the other law of exponents that says a power raised to a power. What's the rule there? Oh, you multiply them. So this is p1 to the 2e1 times p2 raised now to the 2e2. P sub k to the 2 e sub k. These are all even. Notice, 2 e sub I is even, because the e sub i's, are integers, and we're multiplying them by 2. So the other fact was, if we have a perfect cube, if n is greater than or equal to 8, is a perfect cube, then each exponent in its standard factored form is divisible by 3. And you can prove it by just putting a 3 here and a 3 here, and the 3 gets distributed, and you see that every one of these exponents has a factor of 3. And so one of the games that we played was, hey, is a particular integer a perfect square? If so, its square root should be an integer. But the other way to figure out if it's a perfect square is look at its standard factored form, and its standard factored form would have all even exponents. So remember this one. Find the smallest positive integer k. That makes this number, x equals 2 times 3 to the 5th times, say, 5 squared times 7 cubed times 11 to the 4th times 17 to the 7th times k, a perfect square. So we want to build k so that it corrects any of these exponents to make them even if they aren't already even. Remember that kind of problem?
This is another thing that seems like magic that it
Well, the
can be
fact that
done.
we're asked to build k gives us a lot of leeway, right? I mean, we're just asked to find a k that's the smallest one that works, that basically corrects any of these prime factors to make sure that we have an even number of copies of each of those. Once we can make all of these exponents even, then our fact tells us, oh, we're going to have a perfect square. because this proof, even though I couch this fact as an if then, the converse is true. It's an if and only if. If the exponents are all even, then we're looking at a perfect square. If it's a perfect square, then the exponents are all even in the standard factored form. If the exponents are all even in the standard factored form, then it is a perfect square. So it is a biconditional, even though I only wrote one direction. So this is kind of a cheater here in the sense that I didn't make that perfectly clear. Maybe I did. I hope I did in the notes. But anyhow, we want to construct K, okay? So let's look at each one of these prime factors, right? Let's look at P1. It's 2, right? And its exponent is 1. There's a 1 there. Is 1 even?
No.
Factors to add to K. We're going to, build K up. Yeah. This is 2 to the 1. That's not even. We need 2 copies of 2. So we're going to add a copy of 2 to K. All right, so P1 is done. Now we look at the second prime. P2 is 5. No, it's 3. E2 is 5. Is 5 even? No. So we want to throw a copy of 3 into K, and that will correct this 3 to the 5th and make it a 3 to the 6th. What about P3? P3 is 5, and E3 is 2. Do we need to do anything with the 5?
Nope. Looks good.
Yeah,
No.
so yeah, good. It's good, Isaiah. See, it's already even. All right, so P4 is 7, right? We're done with P3. P4 is 7. E4, that exponent is 3. Is that even? No. So what's a factor we need to add to K here? To correct the 7th cube, we want to make it 7 to the 4th. So we add 7.
Yeah, 7. We're
Yeah.
gonna
I say add. It's going to be a factor.
yeah,
All right, so we throw in a factor of 7. All right, what about P5? P5 is 11.
11, in which it's divisible by 4, so it's a perfect square, so we don't need to touch it.
Yeah, its exponent E5 is 4. That's already even. Don't need to touch it. Good. What about prime 6?
6 is gonna be 17.
What's E6?
Um, what's a 7? So we need to add 11.
Yep, so we need to add a 17.
Excuse me.
You're fine. So these are the factors we need to add to K, throw into K. So K is going to be 2 times 3 times 7 times 17. Don't even have to multiply that out. So finally, X is now, 2 times 3 to the 5th times 5 squared times 7 cubed times 11 to the 4th times 17 to the 7th times K, but K is 2 times 3 times 7 times 17. And if we rearrange this and put the 2's together and put the 3's together and so on and so forth, we've got 2 squared times 3 to the 6th. We already had 5 squared. Now we've got 7 to the 4th. We already had 11 to the 4th, but now we've got 17 to the 8th. If we want to really prove that's a perfect square, well, just show that it's an integer squared. And that'll be 2 times 3 cubed times 5 times 7 squared times 11 squared times 17 to the 4th squared. No, that's our n.
Mm-hmm. That's good.
And in fact, it's probably nicer if I make this an n. Make this an n. Although it shouldn't matter.
So for the exponents that are odd, couldn't you just subtract 1 from them?
Well, when the instructions are to build up a k, not to take away from n.
Oh, okay.
But you're right. Theoretically, if we were given a more leeway in the instructions to the game, if the game was fix in, fix in and make it a perfect square by either insertions or deletions, then sure, delete the 2 and one of the 3's, and in fact, delete everything and just make n equal to 0. That's a perfect square. I mean, you see what I'm saying? I mean, it's like We've got to make enough rules of the game that by playing the game, you demonstrate some understanding. But yeah, theoretically, I could say you're allowed to delete up to one of these each, one copy of each. But that's almost a giveaway. Of course, we could play the same game, same n, but now the game is to find the smallest positive integer k that makes this n, which is, 2 times 3 to the whole thing. Just write it down, 3 to the 5th times 5 squared times 7 cubed times 11 to the 4th times 17 to the 7th times k, a perfect cube. So the correction gets a little more interesting when you have to make sure that the exponents aren't just even. Nope, nope, nope. They have to be multiples of 3 for that. See, we need to add 2 2's to correct the 2, right? Bring it up to 2 cubed. How many copies of 3 would we need to throw into k?
1,
And how many copies of 5?
1.
How many copies of 7?
You're fine.
How about 11?
2,
How many? 17.
2.
Exactly. You got it.
A perfect cube, yeah. Yeah, makes sense.
I've even been known on some final exams when I was feeling like getting really gnarly, punishing students for being bad. I would say a perfect quartic, but I would tell them that it's a quartic if n equals x to the 4th, or quintic, or whatever.
Not that bad, but please just don't do that to me though.
Don't worry, it's already at the printer.
Yeah.
In fact, it's already in my mailbox.
Uh,
Final was created on Wednesday. The time and energy that I saved getting to campus, I sat down and banged out the final on Wednesday. 14 problems. Okay, it's 14 questions. You should be able to finish if you know what you're doing and you don't spend a whole lot of time on any one particular problem. You should be fine.
Oh, also, I didn't even get to ask. We're gonna get all that stuff from chapter 1, 2, and 3, right? So, or unit, I guess. But talking about like basic subsets and
Yeah, like arguments. Is an argument valid?
like modus ponens and modus tollens.
Just circuit and the IO table.
Yeah, we're gonna get that right.
Yeah.
Ooh,
Listen, don't worry so much about modus ponens and modus tollens. My job is not to teach you Latin. But if I give you an argument form, you better know the algorithm to figure out if it's a valid argument form. I will tell you that.
okay.
I got it. Oh, that's my pop. I'll have to call him back. Any burning questions left? Let's see what the chat says.
So I'm just refer back to that first exam for majority
Uh-huh.
question. Okay, cool.
You're good. You've been good all week. You are solely responsible for the creation of several videos this week. So your peers should all be taking you out to lunch, man.
I'm not gonna lie, I've been in every office hour this week.
Yeah, you've been good, man. What can I do for you with that first exam?
Uh, whoa, you put me on the spot.
All right, how about I give you one?
Yeah, you give me one. I'm gonna look at test one.
Draw the circuit.
Ooh, all right, cool.
Give the Boolean expression. Or the other thing would be draw or construct the IO table. So there's like, it's that triangle relationship. So there are a lot of ways we can play this game, okay? One way is I could give you the Boolean. So P and Q and not R, or I don't know, P and not Q and not R, or not P and Q and not R. And then of course you've got the Boolean. So there are a couple of things you might be asked to do. Draw the circuit and give the IO table. Or I could give you the IO table right? Let's just do it for two, just input of two, okay? Which is easier than this because that's the input of three.
3.
That IO table is going to have 8 rows, right?
8 rows, yeah.
But here's a 4-row one, which honestly, for a final, it's a little more fair. Given this IO. Oh, my handwriting is starting to fade here. Give the Boolean expression. That's always helpful to be able to have, even if you're not asked to do it, and then draw the circuit. So I think on the test 1, I gave you the Boolean expression. I asked you to draw the circuit and give the IO table, right?
Yeah,
So, yeah.
And yeah.
All right, so the point is, if we look at the IO table first, it doesn't matter what order we do these two in. This is written in what we call disjunctive normal form. Remember that phrase, disjunctive normal form? The beauty of disjunctive normal form is it gives us an exact readout to the IO table directly. Because each one of these parenthetic expressions, these expressions inside parentheses, gives us an input situation, and it's called an input state. So your IO table is going to have 8 rows. 1, 1, 1, 1, 0, 0, 0, 0, and so on and so forth. The question is, what is the output? The minute we see a P, a Q, and an R, we know we're dealing with 8 rows. And we know we've got 8 different, why 8 rows? Because there are 8 ways to choose whether P and Q are false. 2 choices, P is either true or false, 1 or O. 2 choices for Q, it's either 1 or O. R is either 1 or O. So 2 times 2 times 2 that's why we get the 8 rows, right? But look, which row has the input where it's P is true and Q is true and not R is true? What does it mean? Just because we write what's actually true. If not R is true, what does that tell us about R?
If not R is true, then what does that tell us about R?
Uh-huh.
I'm kind of lost. I don't remember.
If not R is 1,
Uh-huh.
then R is O.
Is O.
Because they have opposite values.
Yeah.
Okay? By definition, not R and R are opposite. So when we see P and Q and not R, we're saying P is hot, it's true, and Q is hot, and R is cold.
R is cold, yeah.
So which row is that going to be? Which row?
That's row 7.
2, 3, 4, 5. P and Q, P and Q. P and Q are both true in rows 1 and 2. That's it. P is true, P is hot, it's 1, and Q is hot. So we got to be in either row 1 or row 2. Down in row 7, P and Q are both cold.
So then we're at row 2 then.
Yeah, yeah. Row 2 is that P is hot and Q is hot and R is cold. That's what not R means. It means R is cold. So that means we put a 1 there. Our output needs to be 1 if the input is P and Q are hot and R is cold. That's
Okay.
one of, see what I mean? So that's situation 1.
Situation 1, and then situation 2 would be hot P, and cold Q, and cold R, in which that would be row 4.
That's right. P and not Q and not R. So that means we want a hot output under that circumstance.
And then for our third statement, it would be row 6 because you're getting cold P and you're getting cold R, but you're also getting hot Q.
You're getting it. This is great review. So that means your IO table has a 1 here, here, and here.
And row 2, 4, and 6.
Yep. And then O's everywhere else.
And then the circuit for that. Can we draw a circuit for that? If you went out of space, like sun.
Okay. All right. So PQR.
Yeah.
Right? See if I can fit it in here. All right. So, ooh, look, it's a not R in all 3 of those. So R can get knotted right away because we're only going to be using a not R. All right. This AND gate has got to have a P, a Q, and a not R. So here's P, here's Q, and here's a not R. They're going to go through an AND gate together. Okay, that's 1. All right, here, P and not Q and not R. Okay, so we got the not R. Ooh, but we need a not P. I mean, we need a not Q. So I'm going to make a not Q. We've already got a not R. And we need a regular P. So we bring a P down. All right. And then now we need a not P, a Q, and an R. Oh, so we need a regular Q. So here's regular Q. Here's not R, but we need not P. So let's bring this down and turn it and make it not P. All right. And then finally they go through an OR gate and make yours look better than mine. Now, what if we're given the IO table? That's a crappy looking table. Let me clean this up.
If we're given the IO table, then we could kind of just go off of what in our third row S, for example, we could kind of just go off of we could get the Boolean expression. We could get the Boolean expression purely.
Exactly. Get the Boolean expression first. How do we get it? We look where the ones are.
Yeah. So the ones would be
Here and here.
4, and that would be P and Q, and then it would be or we're looking at not P and not Q.
Yeah, and it's and the and goes across the row because in this row P is cold and Q is cold, but then we OR these together. So it's P and Q will do it, or not P and not Q. I mean, disjunctive normal form, the last operator is the disjunction. It's the or between the parentheses. See, the or always goes between the parentheses. Good.
Question: Are we always between P and Q? But like, let's look. Can we look at the top? Can we look at the top?
Yeah, it's ands in here.
And we're always gonna have ands in there, or there's possibilities.
Well, in disjunctive normal form. I mean, it doesn't have to. Well, I will always deal with this disjunctive normal form because it's the only form that makes sense to deal with. Because it's the form that allows us to go directly from the form to the IO table. And hence, you can get from the Boolean to the IO table back and forth perfectly if it's in disjunctive normal form. Other forms, you play games to reduce them to this disjunctive normal form. You can always get any Boolean expression into disjunctive normal form, but sometimes it takes a bit of doing. But the usefulness of disjunctive normal form, hence it's normal because it's useful and it's universal. You can always get to that form. but the usefulness is obvious. We can read disjunctive normal form directly from the IO table. And stuff that's happening across a given row is ANDed together. Because look, in row 1, this means P is hot and Q is hot. In row 4, not P is hot, so P is cold and Q is cold. So in the rows, you've got ands because all of these inputs are happening simultaneously to build that particular state of that row.
I get it.
So see what I mean? The ands happen across the rows, but then you OR those together. Because if this happens, or this happens, or this happens, if any of these three input states is what's given, then we're going to get a hot output. And that's the exact and only times when we would get a hot output. This is a complete description of the inputs that provide a hot output. In
Got
some
it.
sense, right? This tells us what the machine is doing.
Yeah.
And I will leave it to you to draw the
That's a
little circuit, but it'll only have a P and a Q
small.
because it'll be small because it's only a P and a Q for input.
Makes perfect sense.
Oh man, I'm telling you, you're a hero among men, Isaiah.
I know I'm asking all the right questions.
You really are. I'm
Like,
telling you, you got professor in your future, or some kind of teacher, because you seem to know exactly what would be. All right.
Yeah.
And I guess, why not? Let's reward people for being here. Is this in focus? Be able to decide if an argument form is valid or invalid. Now, I'm giving you that. I'm not going to say, it's 9:40. I have been speaking with you all, and thank you for your participation for 100 minutes. I am old. I am at my max, but that should point you to, I know there's numerous office hours from much earlier in the semester where we talked about argument forms.
This is relating to roles of interest and whether or not
Like P
your
implies Q, Q implies not R,
our
you
premise is
know,
conclusion.
P or R, therefore not Q, something like that, right? Where you have the premise, and I have no idea if this is valid or invalid. Um,
Forming our truth table to where we could decide whether or not the conclusion is like the roles of interest match with the conclusion truth value.
yeah, you only want to look at the rows where all the premises are true. You're right. Those are the rows of interest because we only care. We only care about the conclusion if all of the premises are true. Because remember, this argument form really means P implies Q, ANDed with Q implies not R, ANDed with P or R. If we have all those, then we're claiming we're going to get not Q. So we only care about when the hypothesis is true. And that means we only care about rows of interest in which all three of these premises are actually true. Those are the only rows where we then have to turn around and take a peek at the conclusion. Make sure it's true whenever these are all true. Remember?
Yes. Yep, I remember. I just
All right.
got you talking about it just a little bit.
Make me earn my pay. Make me earn my pay. Oh my goodness. Somebody better bring me a Starbucks tomorrow. Now, folks, get some sleep, eat some protein, right? Do something to relax, listen to music, take a long soak in your soaking tub, whatever you do, make sure you get some good rest because that's going to serve you as well, better than pulling an all-nighter. You got to trust me on that. No good has ever come of pulling an all-nighter. Work to a reasonable hour and then get some sleep.
What's the protocol for going into the exams, just to make sure I kind of know what to expect? Show up with two forms of ID and
Yeah, you
my
gotta
birth
have two
certificate and
birth
every.
certificate. Oh yeah, aren't you funny? And there's a fee, there's a small entrance fee, that's
Mhm.
double if you're late. And
We have
then
to
there,
sit in a courthouse waiting
yeah,
around for a
oh
few
yeah.
hours.
I'm gonna have my wig on and my robe. I'll wear my regalia tomorrow just to scare everybody. And we'll show them how it's done in the court of final exam. No, the main thing is we're stuffing a lot of people into a fairly large room. Mo Listen, the folks that are in this office hour right now are not people that I'm worried about. Okay, are there people who, might take a peek at something that they shouldn't be taking a peek at? It's possible. Do I like playing policewoman? No. Is it part of my job? Yes. So I'll just separate everybody so that I can do that without, having to, bug people. I'll do that at the front end. I'll make sure everybody's spaced out, make sure you got enough elbow room. You can go ahead and put your phones away if you have a bag. Uh, I've had people, get their phones out on tests and, and try to look surreptitiously online. You know, that happens. And I know it's not going to happen with anybody in the room here because you wouldn't be in the room if you were that sort of individual. But, point made there, Jonathan. It's an unhappy truth of the job. I try to be fairly good humored about it. But cheating is something that, I come from a long line of teachers. My grandmother was a teacher. My mother was a teacher. My pop was a university professor. Cheating is just like it's the biggest no-no in my family. So I kind of take it personally. So I just like to try to nip that in the bud. So yeah, I think I know everybody that's in this room, but there are a couple people that there are definitely a couple of people that only show up for exams, and I think I know all their names by now. But if you only see
Is
somebody 3 times a year,
just to make sure then, joking aside, we have to have our ID, a calculator, no cheat sheet. I saw your note about that,
yeah,
and
you won't need a cheat
pe
sheet.
pencil and
Plenty of
uh,
pencils, several pencils.
okay. And
I will
will
provide
there be a
scrap
provision
paper.
for scratch paper? Okay.
Yeah, there's one stapled already to the back of every test, so I won't have to hand them out, but I will have extra if you need it.
Okay, dope.
Use the
Thanks.
facilities before. I think it was last semester. I had a kid who got shit-faced drunk the night before the final, and he was so sick he had to like go into the bathroom numerous times just to be sick. Poor guy. Like you don't want to show up like hungover like that. Save that for tomorrow night.
I
Oh,
have a question.
yeah, Rebecca.
You said that the final grade, if is better than one of your exams, you're going to replace that grade, correct?
That's right. If you sat for all 3 exams, and your final is better than any of those, I will replace your low exam grade with the average of your final exam. I sure will do.
Okay. And
And
then, let's hypothesize. Let's say you don't. Would the original deal still stand?
yeah, I mean, if the final doesn't help you, I'm not going to make that substitution. I'm going to give you the higher. I'm going to give you the highest grade I possibly can.
Okay.
That the option is there if it helps you. I'm not going to exercise it if it doesn't help you.
Okay, thank you.
Yeah, and but so this is a great opportunity to this stuff is tough, right? This material is not trivial. It's deep. It's we've covered a lot. I think we've done a pretty good job moving at a steady pace. I don't think that, we got all bunched up anywhere in the semester. So I think We've done a really good job covering everything, plus more. We actually covered more than a lot of other sections covered because we covered stuff on circuits and we covered stuff on recurrence relations. And so I think we did a really good job moving through the material. Y'all worked hard. Those special homeworks, they were not trivial. You worked hard this semester, and hope that everybody gets out of here with a decent grade, and that I only see you visiting to visit or in another course. I'm not the kind of person that holds you to one point. You know what I'm saying? A certain percentage is a C, and you're a point away. I'm gonna give you the C. I can't give you a C if you're at a 45. Okay. But, I can probably give, I'm a little lenient. I better stop recording before I get myself in trouble.